Hi everyone, we're going to do a rundown of Unit 5, which is on torque and rotational dynamics. This is also known as angular kinematics and torques. So kind of like Unit 1 and 2 that we did in rotational form. So this is going to be broken into 6 sections. The first being on rotational or angular kinematics. We're going to be trying to look at the different axes that we have, that tangential, centripetal, radial, translational, etc., and seeing in what ways we might connect linear quantities to rotational quantities. How do they overlap and relate to each other? In 5.3, we introduced the concept of torque, which is like rotational force. Rotational inertia is 5.4, and that's basically the rotational version of mass. So it's how difficult it is to spin something, in the same way mass is how difficult it is to accelerate something in a line. 5 and 6 are going to relate to equilibrium conditions, meaning like when you have, instead of balanced forces, in this case you have balanced torques, and 5.6 would be when you have unbalanced torques. And so without further ado, we're going to run through the notes we have from this, and I'm going to try and emphasize the concepts through some of the examples that we'll look at. We're not going to ink out any examples, we're just going to look at some and again, emphasize concepts that we have. If we look at the single page approach sheet, which this is going to serve as an outline for us. So torque problems are going to be the main focus of this unit, as most people find kinematics to be pretty straightforward. We'll still look at it though. So you can smell out torque problems, especially when you have problems not involving necessarily linear acceleration, but more so angular acceleration. It should be noted though, in general, when we want acceleration or are involving acceleration, that's typically going to indicate a force problem. And if there's rotation as part of that situation, even though it asks for acceleration, we will probably have to use torques as well. So I put here that problems involving linear or angular acceleration and other classic force types, quantities like mu, other forces are given mass, etc. The word equilibrium implies balanced forces, but also balanced torques. And so equilibrium is often a trigger word to use forces or kinematics. And you'll often see like systems like pulleys and things like that that have strings and ropes in a lot of torque problems. And what we're going to do, just like force problems, is draw a force diagram. We could get away with the free body diagram, which we draw all the forces acting from a single dot back in the force unit, but we're going to probably want to do force diagrams in this unit because where those forces are acting, the point where those forces are being applied, is really important to torques. We're going to need to define if there is an angular acceleration. We're going to let that direction, as clockwise or counterclockwise, be the positive direction for rotation, just like we did for linear acceleration, defining the positive direction as more force was that way for those linear force problems. And we're pretty much going to do, in addition to forces, we're going to do torque. So we're not necessarily only doing torque or only doing forces. It's kind of like forces and torque. So we can do still linear forces in a torque problem. It's almost like an add-on. There are a lot of absolute truths. Some people find these to be helpful. Some people just, it's too daunting to look at some of these, but there are 17 statements that I can say are always true about torque and angular kinematics. So we'll revisit some of these, but if you'd like, you can take a look at some of these and make sure that you know that these are always true. And we're going to echo all of these points as we look through. So a quick math refresher to start us off with rotation. Our angular displacement is, instead of meters like linear displacement or distance, angular displacement, how far you turn, is theta, and it's measured in either the number of rotations you're taking, degrees, or radians, and we're going to be using radians as our standard units, as we should know right now. A quick refresher on a radian. If we have a radius and you take that same distance, let's say it's 2 meters, and you have a perimeter traced out, or an arc of 2 meters, same as the radius, then the angle is going to be 1 radian. So for example, if we had the arc length, the amount of perimeter was the same as the radius, 2 meters, we made the radius as well, 2 meters, those 2's would divide out and leave us with theta equal to 1. When we trace out how many of these 1 radian angles fit into a full circle? We of course get 2 pi, or as decimal, 6.28. And that's what we're going to use as our base for unit, our base unit for theta. Now, it should be note worthy here that this arc length equation is the core relational equation between a tangent axis here, so tangential quantities that are along a tangent line along the perimeter, and the angular quantities with a base unit of radians, like theta, omega, alpha, so that like V tan is equal to R omega. Everything's predicated off of this arc length idea, which is why I'm showing this right now. And as we know, when things turn, they can go clockwise or counterclockwise. And so for horizontal, where we had right and left, defining positive and negative, and vertical, we had up and down, defining positive and negative. For rotational, we use positive and negative to define clockwise or counterclockwise. And these can be used interchangeably. You don't have to have up be positive, although that's kind of the default thing. Same thing with to the right. We can make that negative and to the left positive, but generally we default to these directions. So in terms of key concepts here, we should be good on all of these quantities here. You may want to pause and just make sure the math concepts are all familiar to you. But what's different about with AP Physics is we have a lot of now axes that we can worry about here. So before we were just doing linear, like x-axis and y-axis stuff. That is not just linear, but more specifically translational. That represents the straight line motion of an object's center of mass, or we can say of for a rotating object, the pivot point, which if it's just rotating is going to be stationary. But if that pivot moves, then that motion is described as translational. So for rolling objects, the translational motion and the spinning motion are synchronized. For angular or rotational motion, obviously that's spinning around the center point. That's going to be your theta, omega, alpha, right? Now, tangential and centripetal are for circular motion. Notice they're both for circular motion. So it's not that you have a spinning object. You have to have an object that's moving in a circle, or a point that you're looking at that's moving in a circular path. So it has to have a radius to its circular path. It's not just a spinning object like a disk with a radius. It has to be a point mass or a point on a disk that we're tracking as it moves in a circle. Then it would have two things here. We'd have tangential and centripetal. And looking at this example back from Unit 2, when we did circular motion and first introduced these axes, if you have a circular path around, then you would have a tangent line, which defines our tangential axis. That represents the circularly moving objects forward and backward. So if it's speeding up, we would have an acceleration along the tangent line. If it's slowing down, we would have an acceleration that's pointing against the velocity's tangent line axis, right? The radial axis, meaning along the radius, which would be like inward or outward, is also necessary for us to have this circular path for us to really worry about. Of particular interest would be any point or mass that's moving in a circle would have to have a centripetal acceleration. If it's speeding up or slowing down, it would have, in addition to a centripetal one, it would also have a tangential acceleration. Okay, so pointing out those, a net force or acceleration with or against the velocity along a tangent line would create speeding up or slowing down. If it's moving along a circular path, that being a mass or a point is moving along a circular path, it has to have a net force or acceleration inward because it's changing direction. So going back to our types of motion, for circular motion, tangential is going to represent our linear velocity for an object that's moving around a circular path. And the centripetal is going to be the inward direction that is associated with the centripetal force or centripetal acceleration, which are the net force inward and acceleration inward for any object that's moving in a circle. It's the acceleration due to its change in direction. Just as a visual, we can use a rolling object here. So if this object is rolling, it's going to be then spinning clockwise. So you can see here, first and foremost, let's look at the rotation of this. So we have the omega, which represents its clockwise motion. And that is entangled with the V-tan, meaning these are related to each other. If I have a bigger speed rotationally, then I'm going to have a bigger speed tangentially. Right? In fact, this equation, V-tan equals R omega, is what relates the tangential velocity at some point that's moving in a circle and how it relates to the rotational speed omega. So that's going to be a really important one for connecting a tangential motion of something moving in a circle to the omega, which could be the spinning motion of the object it's connected to, or if there's a dot on a disk, then the tangential velocity of that dot would depend on how quickly the disk is spinning. The blue here, which is translational velocity, assuming this is rolling along a straight line, is tracking that center point. So it would be tracking the pivot, which is at the center of mass, and that's that straight line rolling motion that we would study in units 1, 2, 3, or 4, just that straight line path. Now, I've drawn it here at 3 different points because really the object, the sphere here, is going to be rolling, so any point on this is going to have a translational speed. They're all moving, right? All those points in the ball are moving. So I'm drawing it down here, though, to show that the tangential velocity due to the spinning is clockwise, which is to the left when it's tracked from the bottom. And the translational velocity is always to the right here. And so if those are balanced, then they essentially cancel out, and the overall vector for the velocity at the bottom is 0. It doesn't mean the object is 0, it means the point of contact here is 0, which means there's no slipping or sliding at this point of contact. And that allows us to replace the tangential velocity with the translational velocity when there is no slipping as it's rolling. This is really important in Unit 6 as well. So there's a couple different examples that we studied here. So if a bug is inside the rim of a hoop that's rolling down an incline, what of the following vectors are there for velocity? And so angular, yes, there would be an angular velocity here, right, because it's spinning. Because we're tracking then the bug here, which is on the inside of the rim, that would be moving in a circle. So it would have a tangential velocity. And this also has a translational velocity since the hoop, which the bug is glued to or attached to, that center of mass, or the pivot point in this case we could think of, is moving in a straight line. So it would have all three of these. If we consider the accelerations of just the bug down here, then the spinning motion is speeding up, and so this would have an angular acceleration. Since it's speeding up rotationally, then the tangential velocity is going to increase, meaning there's a tangential acceleration. And there has to be a centripetal acceleration even if it's constant velocity. There has to be a centripetal acceleration if it's turning. So if it's traveling a circle, there has to be a centripetal acceleration. So the overall vector of those two should be the hypotenuse of the red and green arrows. And the translational motion of this, meaning is it speeding up as its center of mass or pivot point moves down the incline? Yes, its translational speed is speeding up. So we'd have all four of these accelerations. In contrast, instead of tracking the bug as it moves in a circle, if we were just looking at the hoop, it would have the same acceleration as the bug, angularly, because they're rotating as one. But since the hoop is not a circle, it's just an object, it's not moving in a circle. We're not taking the hoop and moving it in a circle, right? Or this way, in a circle. It's just spinning in a circle. So it's rotating. So the fact that it's spinning and not moving in a circle means there's no tangential or centripetal motion for that reason, right? And then translationally, we just said that it's moving, its center mass or pivot is moving down the ramp, and so therefore it has translation. In 5.3, we looked at torque, and so we have this official definition of torque is going to be how much of a twist that we have, the force that causes rotation or is trying to rotate an object. And so for a force to try and turn an object, we have to have a force that is a distance r away from the pivot. In addition to that, we need to have that force be perpendicular. So if I wanted to turn this door, if this is an above view of a door and the hinge is right here, I would have to apply that force away from the hinge, some distance r, and as perpendicular as possible. If it's at an angle, then we have to account for the perpendicular component of the force with respect to r. So more force, more torque. Farther away from the pivot, more torque. And perpendicular will maximize that. So for that reason, we can calculate the individual torque due to an individual force by doing the distance from the force's point of application where it's being applied. That's why it's really important on our force diagrams to draw where that force is being applied. Because that point to the pivot is R. How much force we have obviously is F. And then sine of theta is going to ensure that we're using F sine theta. That's going to be the perpendicular component to R. As long as we use a theta, that's the angle between the axis defined by R. So if we were to draw a line for R, you can see here this would be horizontal for this example. And if we draw an axis through F, that would be vertical, so the angle between them would be 90. But you can always think of the axis along R and the axis along F. Angle between them is what we're going to use for the angle in this equation. We need to ensure that those two vectors are perpendicular, or we're using a perpendicular component. In this example, you can see we have a force that we're pushing with, F, that we're trying to solve for. Since this force is being applied perpendicular, we would not have a sine theta. We would use R to be the distance from the pivot, which it says it's at the 4 meter mark here, to 0, so we used 4. The force from the pivot point is not going to have a torque because there's no R value. The R is 0, really, right? There's no distance from the pivot to where the force is being applied. That will disregard this force from our torque analysis. It just simply doesn't exert a torque. And the force of gravity, which acts from the center of this rod at the 5 meter mark, since the overall rod is 10, the middle of it's 5, and mg acts straight down. Since the rod is tilted, then I have to use not only the distance of 1 and the force, I have to also use sine of the angle between. And so if you notice here, I'm using the radius r along the rod and the force mg to be the axes that define the angle between of 60 in this case. I couldn't use 30 because that's not the angle between these two vectors. In 5.4, we learned about rotational inertia. Now, rotational inertia can be very straightforward, where we just are given the value of it, but it's going to be important to make sure we recognize also conceptually what we are going to be asked about and what are the more difficult variations that we have that maybe aren't as straightforward as just these values we see in front of us here. So probably have most of these memorized. We're often given these in problems, but each shape of the object, sphere, disc, hoop, rod, are going to determine the rotational inertia equation. Now, conceptually, smaller rotational inertia means that it's going to be easier to angularly accelerate something, right, to get it to start to spin. So this is kind of like mass, where mass is how difficult it is to get it spinning. Rotational inertia is how difficult it is to get it to spin. So a smaller rotational inertia like sphere here is going to be easier to spin than a hoop. Now, conceptually, what we want to make sure we understand for ranking purposes and things, what makes something harder to rotate is it has more mass that is, on average, located farther away. So if you think for a second, a solid sphere versus a hollow sphere. A solid sphere we know is 2/5 mr squared. So we expect a hollow sphere to be greater I value or a smaller I value. And so if it's the same mass and radius, a hollow sphere is going to have the mass on average located farther away because it's all located on the outer edge, right? So for that reason, it's going to have a greater rotational inertia than a solid sphere where the average mass is going to be located closer to the pivot. And that's true for all of these objects. Therefore, the easiest location that we can put our pivot and have an object spin would be at the object's center. That's why all of these objects are defined as having an I value based on a pivot at the center. It's the smallest I value we can get for each of these individual objects. It should also be noted here that a hoop and a mass moving a circle are the same because in both cases the mass is located on the perimeter of a circle. So whether you have a point mass or a hoop that has a mass on its perimeter, they're essentially rotationally the same in terms of their rotational inertia. So what would happen if we take any of these shapes and we shift the pivot over to the side, away from the center of mass? So if the pivot's not the center of the object, it's always going to have a greater rotational inertia, because now the mass is going to be on average farther away from the pivot. In those situations, if it's just simply shifting it over, we can apply what's called the parallel axis theorem, because we're going to be rotating it not through the center, but through a parallel axis instead. So the distance between them is going to be d. It's displacement of the center point to the actual pivot point. So for example, if we were to, instead of having a rod pivoted about the center, if we were to shift that pivot point over to one of its ends, like the left end here, notice that it's going to have a higher I value. So instead of 1/12 ml squared, it's going to be 1/3 ml squared. And this equation is going to allow us to calculate that value, as we'll show an example here in a moment. So we take the baseline, what's the smallest amount we can get, which would be if the I were through the center of mass. And we're going to add some additional rotational inertia to it because it's not through the center of mass. Right? If d were 0, then we would just have the center of mass. So d being how far it is from the center of the pivot point must be non-zero for us to even use this. Of course, we also have, for non-uniform rods, potentially we could do discs on this using annular rings, but we typically see this very often with non-uniform rods where we're given linear density, and you have to integrate that in order to do that, as you'll see in other examples throughout our review. I wanted to show you how to derive this 1/3 ml squared using parallel axis theorem as a quick example. So if we look down at number 8 over here, in this case we would have a rod that's pivoted about its center point, about its end, and so we would take the I value, if it were at the center, the 1/12 ml squared, and we're going to add md squared. The distance d, which is the center to the new pivot at the end, is going to then be defined by L/2. If we square that, we get L squared over 4, which is the same thing if we get common denominator 12, 3/12. When we add that, we get our 1/3. We could do that also with really anything, right? So if this is at 1/3 of the way from its end, start with what it would be if it were through the center, and then we're going to add md squared. In this case, the distance from our center point to our new pivot is L/6. So we have to then put that as d. If we have multiple objects, let's say we have a rod and there's a mass glued to it, then we would have to take, based on the pivot, this is at the center of the rod, so we'd have 1/12 ml squared. And then we would treat this same pivot point, we have a block over here, point mass, that's going to rotate in a circle, so that would have mr squared, and we just add them. Just like if you have multiple blocks tied together with a string in a force problem, they would move as one. And if we were treated as a system, we would just add all the masses together to get the total system mass. Here, this is rotating as one, so we'd have to get the total rotational inertia of the system by adding up each individual object. If we start to look at examples of typical situations we see, a lot of times we can see pulleys or rolling objects. So if we start with pulleys, then do we treat these as a system like we did in Unit 2? Short answer is no, we can't, because the linear system requires everything's moving linearly as one, right? They all have the same linear acceleration. Rotational system would require that all objects are glued together and like rotating as one. So in a pulley where you have a point mass here attached to a string that goes around a pulley, the pulley is rotating, but its center is not moving translationally. The block is moving translationally downward, but it's not spinning. And so they're related in that the tangential motions are the same here, but we cannot treat these as a two-object system. We have to keep them separate. It is always true that the tension between two objects, where two objects connect to a mass, is always the same. And so we can apply that logic here, but if there was an object hanging on the other side, that would segment this one rope into two sections. The one on the left would have the same tension, which would be different than the tension on the right side, which would be the same for each end of that segment of rope. So if we look at this example, if we separate these, the boxes can represent the strength of these. I would always do a working diagram off to the side, just identifying the forces, then start to think, all right, so are these balanced or unbalanced, to make sure I can draw more boxes if they're unbalanced, or equal boxes if they're supposed to be balanced. So in terms of the forces acting on the pulley, we have a force from the axle that's holding it up, gravity's down, and this tension force is acting down. The hanging object is going to experience that same tension force and a downward force of gravity, and I know that m2g has to be bigger since there's an acceleration downward. I know the tensions have to be the same, so I'm going to have to use the same number of boxes for the tension. I need to make the m2g bigger than that tension, and I need all the vertical forces to balance out for my pulley because it's not translationally accelerating up or down. So I need to have the total number of boxes up equal the total number of the boxes down for these two forces combined. You can see I need to keep these objects separate, but what I can connect with them is that the translational acceleration of the block down is the same thing as the tangential acceleration of the pulley, since the string attached to the block goes around the outer perimeter of the pulley. That's an important thing because that allows us to then say that the tangential acceleration, A, is the same thing as the translational acceleration of the pulley. They're the same A. And that will allow me to create a similar or common variable, common term for these things to be then merged together. And I can ultimately solve for A, or I can solve for alpha. As a compare and contrast with the Unit 2, where we had massless pulleys, I would treat this as a linear system if this was a massless pulley. That allows us to eliminate the internal force of tension, which would be the same upward on M2 as it is upward on M1. Those would point actually in opposite directions, though, if following positive is being down, and positive here, positive down on M1, which means that positive is up on M2 as they move, so that those tensions would actually be in opposite directions. But since they're internal, we don't include them as a system, and I could easily solve for acceleration as a system. If this pulley has mass, it changes it all because we can't treat it as a system because not all the objects have the same linear acceleration. So I'd be forced to treat these separately. As mentioned before, the tension on the left side would have equal tensions from both points of contact, but to be different or to be segmented in different tension from the right side, which would have the same tension on the pulley and on M2. Make sure that you don't ever say that the M2G pulling down is what is pulling on the pulley, because we know that M2G is not necessarily always the same as tension, right? In fact, this case it's not. M2G is bigger because there's an acceleration down. So be careful not to fall victim to that. If it's a string that's pulling down the pulley, it's a tension. You would have to then justify the tension and gravity are balanced in order to say that the tension pulling down is the same as the weight. In general, we don't want to do that. So it just creates extra math for us to look at in order to solve this problem. For rolling objects, we would do, again, a force diagram. In this case, we're solving for acceleration. So this would normally be a force problem. I will know, because there's spinning involved, that I probably will also have to use torque in addition to it. And so if I do x forces alone, you'll see that the reason for us having to do torque is because we're going to be left with two unknowns. It's a static friction. We've already talked about the fact that this would have a static, meaning non-slipping, point of contact if it's rolling without slipping. So that means that the friction has to be static. We cannot use that mu equation unless that static friction is at its maximum. Very, very common mistake. Don't put mu times normal force in for this because it's not at its maximum and it's not sliding. So mg sine theta is down, friction is up. It's a static friction. We can set that equal to ma. We have two unknowns. So I'm going to go to torque. Now, normal force is acting at a distance r away, but it's not perpendicular, so there's no torque due to normal force. Mg and its components are actually acting from the center. Therefore, they do not exert a torque on this object. Friction is the only force that exerts a torque. Therefore, we need friction to synchronize the translational motion with the angular or rotational motion. So if the object speeds up translationally, it has to spin faster. Friction is what allows that to occur. Otherwise, if you don't have friction, the rotating motion is going to just remain fixed. There's nothing to cause it to change its motion or even to start rotating in the first place. So it would be a completely different story. So the friction here due to the torque due to friction is going to be the r, the radius of it, times friction. And we'd have the I value that can change depending on the shape of this. It's a disk in this case, so it's 1/2 mr squared. And notice here that I replaced the alpha with a over r because I'm solving for a. So I wanted to put alpha in terms of a, and this should be a tan over r. I can make it the same as the translational acceleration as long as it's rolling without slipping. You can see here it's the exact same approach if we use a hoop, just mr squared. And same thing if we use a sphere, except 2/5 mr squared. And the last thing we're going to actually come back to here, because this is technically 5.5, and we were looking at some unbalanced forces first, is static equilibrium. Now, static equilibrium is going to imply that all the forces and the torques are balanced. So our net force is 0 and our net torque is 0. In this case, we don't actually have a well-defined pivot. Even if there is a pivot in the problem, it's not a well-defined pivot because there's no angular acceleration or angular motion at all. So if that's true, then our torques have to be balanced no matter where we place a pivot. So we can really choose it to be anywhere. Strategically, we want to put this at a point where there is some unknown force or undesirable force, because then technically its torque is 0 if we have that force acting at the pivot. And we can generate as many different torque expressions as we want just by replacing where we're defining the pivot point or r equals 0 to be. We can also do force problems, but those force problems are going to have those undesirable forces in it potentially. So torques actually present an advantage since we can eliminate unknown and unwanted forces by placing a pivot at the point of application. So for example, if we're trying to, let's say we're trying to solve for the force F2 on the right side. If we don't know the force on this left side, then I can place the pivot there, meaning r equals 0, and I would do a torque expression where the only force I don't know is F2. The rest of these weights would be known, and I don't have to know the force here. If I did forces vertically, I would have both of those forces as vertical forces present, and that would create two unknowns that I could not solve. So torque is at least required here. In this classic type of problem here where we have a hinge, yeah, there's a pivot here, but if it's not actually spinning, it's not a well-defined pivot, which allows me to choose any point on this rod to be my pivot point. If I didn't want to solve for this hinge force, because it can be vertical and horizontal, meaning it's at an angle, and that presents a really annoying problem potentially, and I just wanted to solve for tension, then placing a pivot here would be great, because that eliminates this undesirable hinge force and allows me to solve for the tension, as you can see here in the blue part. By placing the pivot where this tension force is, I could eliminate tension and focus in on what the hinge force is. Notice with torque, since I like perpendicular forces with torque, I would be getting the component that's perpendicular when I get the hinge force using torque, which is what I'm doing in this green part here. And I could still use forces horizontally, for example, to get this x component here. So the x component of the tension and the x component of the hinge force would have to be balanced. And that would allow me for me to solve for it. Another option would be to use vertical forces, where I'd have to know tension, and I could get the vertical component of tension. And with knowledge of both of these gravities, I could figure out then what this hinge force would have to be using forces. So we're going to just network a bunch of system of equations together, just like we would whether it's balanced forces or unbalanced forces and torques, but with the equilibrium allowing us to choose a pivot point wherever we like. Thanks. I hope this was helpful, everyone. Let me know if you have any questions.